With 10 million bamboo poles mobilized, an astonishing amount that, laid end to end, would be enough to wrap around the Earth twice, engineers in Indonesia are carrying out one of the boldest infrastructure gambles in history to save a coastline that is slowly sinking. Instead of pouring billions of dollars into steel piles or ultra-strong concrete structures to resist the relentless force of the Java Sea, they are placing the fate of a 27-kilometer-long expressway in the hands of this wild-growing grass. But how can a seemingly fragile network of hand-woven bamboo mats be pressed beneath the seabed and completely replace rigid metal foundations? Don't blink. Join Mandarin Tech as we step inside this massive construction site and discover how human ingenuity is tearing up the traditional engineering rulebook. The North Java coastline is being battered by dozens of severe floods every year, threatening to swallow entire low-lying areas. To stop this disaster, the 16.8 trillion rupiah Semarang Demak megaproject was launched with a dual mission: to serve as a modern expressway that can cut travel time by 70%, while also acting as a massive seawall protecting thousands of lives. The entire route stretches for nearly 27 kilometers and is divided into two sections. The 16.3-kilometer Semarang Demak section has been in operation since 2023, while the remaining 10.6-kilometer Semarang Siang section is where the real engineering challenge begins, because the coastal ground is simply too weak to directly support the enormous weight of an expressway. It is here that engineers selected 162 native bamboo species to create an extraordinary feat of economic engineering. The solution not only helps Indonesia save billions of dollars in construction costs and protect the marine ecosystem, but also avoids disrupting the busy fleets of cargo ships operating day and night right alongside the edge of this massive construction site. Behind the convenience of modern life lies a mountain of material waste expanding at an alarming rate. According to the OECD, humanity produces more than 400 million tons of plastic every year, yet only about 9% of global plastic waste is actually recycled. The rest is burned, buried in landfills, or leaked into the environment, where it can remain in soil and oceans for decades. The search for alternative materials has therefore become increasingly urgent. And among a growing wave of new technologies, one surprisingly old candidate is making a comeback: bamboo. Botanically, bamboo belongs to the grass family, yet its stems can become woody, grow rapidly, and regenerate after harvesting. China is now home to more than 800 bamboo species and has developed a processing industry worth hundreds of billions of yuan, creating a large enough industrial foundation to move bamboo beyond traditional workshops and into mass production lines. In 2022, China and the International Bamboo and Rattan Organization launched the Bamboo as a Substitute for Plastic initiative. One of the most visible products to emerge from the shift away from plastic is the bamboo straw. The raw material is typically selected from bamboo culms around 2 to 3 years old, when the walls are strong enough for use, while the stems are still relatively slender and easy to process. After harvesting, the bamboo is cut into short sections. The internal nodes are drilled through to create a continuous hollow channel, and the pieces are then placed in drying chambers at around 70 to 80 degrees Celsius to reduce moisture and improve dimensional stability. Once dried, each straw is polished on both the inside and outside to remove fibers, sharp edges, and rough surfaces, while both ends are smoothed for safe contact with the mouth. The straws are then washed with a disinfecting solution, dried again at around 25 degrees Celsius, and inspected for diameter, straightness, and surface quality before being sorted. Products that meet the required standards can then be laser engraved with logos and packaged for distribution. From a simple piece of bamboo that undergoes almost no complex chemical transformation, just cutting, drilling, drying, and mechanical finishing, it becomes a reusable product capable of directly replacing single-use plastic straws. More complex than bamboo straws is an entire range of tableware made from bamboo fiber, from food containers and plates to cups and spoons. At factories in Chongqing, Bamboo is chopped into small pieces, treated with steam to break down its structure, and then ground into fine fibers. The fiber mixture is transferred into molds and compressed under high heat and pressure to form finished products. After roughly 18 processing stages, from coarse grinding and fine milling to molding and antibacterial treatment, raw bamboo can be transformed into tableware that is heat-resistant, water-resistant, oil-resistant, and capable of withstanding temperatures as low as -40 degrees Celsius. And the scale of this replacement is anything but small. In 2024 alone, China consumed around 84.9 billion single-use food containers, creating an enormous market that bamboo fiber products are now seeking to capture from plastic. Sophisticated food containers and bamboo straws have already demonstrated the remarkable versatility of this organic material. But no matter how advanced a heat-press plate may be, it only has to carry the weight of a meal. The true mechanical potential of this hollow stem plant emerges only when the load placed upon it is no longer measured in grams or kilograms, but in millions of tons. And to witness that almost unimaginable limit, we now leave behind the sterile factories of China and head straight toward the brutal front line of the ocean, the Semarang Sayong mega project. The 10.6-kilometer section stretching across the Java Sea is more than just a construction challenge. It is a graveyard for conventional foundation methods. Beneath the breaking waves lies one of the project's toughest engineering obstacles: a layer of water-saturated marine clay, soft, unstable, and possessing almost no load-bearing capacity. Faced with what seemed like an impossible problem, Indonesian engineers made a bold decision: drive bamboo piles into the seabed. This was not a cheap temporary solution, but a carefully calculated piece of structural engineering. Bamboo possesses two powerful advantages that steel simply does not: natural buoyancy, created by its hollow structure, and remarkable tensile strength, provided by its longitudinal fiber system. Instead of fighting against settlement directly, engineers turned bamboo into a gigantic pair of snowshoes for the expressway. By weaving millions of bamboo poles into enormous mats and pinning them into the soft mud with vertical bamboo piles, they created a vast, flexible load distribution layer, capable of spreading the enormous weight of the highway across a much wider area. Emerging from the tropical forest, the transformation of this giant grass begins with a strict selection process in geotechnical laboratories. Not every bamboo pole is chosen. Only those that have grown for a full 3 years, measure at least 8 meters in straight length, and have a diameter of no less than 10 centimeters are accepted. There, they must face specialized hydraulic machines for horizontal tensile testing to measure their resistance to pulling and tearing forces, as well as perpendicular bending tests to evaluate their remarkable elastic capacity. Once the material is ready, the vast construction site on the Java Sea is transformed into a magnificent picture of manual labor combined with mechanical thinking. More than 1,500 skilled workers are mobilized to carry out what seems like an impossible task: weaving a gigantic shield directly on the water surface. The process begins with a vertical foundation system. Instead of driving each bamboo pole individually, the engineers designed a modular load-bearing system in which every 7 full-length bamboo poles are tightly bound together with a specialized rope system to form a super-strong pile cluster. Tens of thousands of these pile clusters are then driven vertically by machinery into the soft mud, arranged in a grid matrix with a precise spacing of 1 meter. This pile network does not only extend along the route, but also spreads outward on both sides to a width of up to 150 meters, creating a massive buffer zone beneath the sea. Right on top of these tens of thousands of piles, the second stage of the system begins to take shape: the reinforced bamboo mat layer. The highest quality bamboo poles are woven in crossing patterns, tightly lashed into enormous raft-like mats, and laid flat to cover the entire surface of the pile matrix. Using highly precise manual knotting techniques, workers lock the mat surface onto each protruding pile head, merging the entire vertical and horizontal structure into a single unified mass. When the final binding line is tightened, this colossal piece of biological architecture begins to slowly sink under its own weight in the pressure of the current. It descends into the dark sediment layer below, silently locking the water-saturated mud in place. And the miracle is that this structure does not simply disappear. Over time, the submerged bamboo mat network can evolve into an artificial reef, where marine life attaches, grows, and multiplies, creating a perfect symbiosis between a human infrastructure marvel and the ocean's original ecosystem. Once the bamboo pile system and bamboo mats are complete, the project moves to the next stage, covering the entire foundation surface with geotextile fabric. Large rolls of fabric are laid continuously along the route, with some sections extending across a width of up to 150 meters. Each sheet is stretched, leveled, overlapped, and carefully secured to prevent displacement during construction. This geotextile layer forms a separation barrier between the bamboo system below and the sand fill above, preventing material from falling through the gaps, reducing the mixing of sand with the weak mud underneath, and helping distribute the load more evenly across the foundation. Once the covering layer is finished, millions of cubic meters of material begin arriving at the site. Offshore in the Java Sea, trailing suction hopper dredgers travel to designated dredging areas. As the vessels move slowly, large suction pipes are lowered to the seabed, drawing a mixture of sand and water into storage hoppers inside the ships. There, excess water gradually drains away, while the sand settles until the hopper reaches the required load. The vessel then heads toward the construction zone. High-capacity pumping systems force the sand and water mixture through pipelines toward the road foundation, creating continuous streams of material flowing across the geotextile surface. Bulldozers and grading equipment immediately spread the sand outward, adjust the elevation, and form controlled layers of specified thickness. Trip after trip, dredgers at sea continuously transform sand from the seabed of the Java Sea into a massive artificial embankment, gradually raising the construction platform in preparation for the expressway structure above. This cycle of offshore dredging, transportation, pumping, and layer-by-layer grading is repeated continuously along approximately 6 kilometers of the weakest ground, steadily raising and widening the roadbed. However, the enormous weight of the sand fill also presses heavily on the water-saturated clay and mud underneath. If left to settle naturally, the consolidation process could take many years and cause the road surface to continue sinking even after the expressway opens. To prevent this, engineers install large numbers of prefabricated vertical drains, or PVDs, deep into the ground. Under the pressure created by the sand embankment, water trapped inside the soil pores is forced toward these vertical drains and then discharged upward. As the water gradually escapes, the soil contracts, becomes denser, and gains greater load-bearing capacity. In other words, engineers deliberately force the ground to settle in a controlled manner during construction, instead of allowing that settlement to occur after the expressway has already entered service. Once the underground foundation has been brought under control and stabilized into a rock-solid platform, the mega project finally rises above the water and begins to take on its final form. The enormous responsibility of carrying the load now rests entirely on the bamboo and sand foundation system below. Above this biological platform, engineers first lay a crushed stone subbase using sharp-edge aggregate to lock the structure in place and suppress any remaining ground movement. This is followed by the upper base course, combining granular material with strongly bonded bituminous layers designed to distribute the immense pressure generated by heavy trucks and continuous traffic. Finally, a smooth layer of black asphalt pavement is laid across the surface, completing the last mechanical layer of the expressway. But the true masterpiece of the Mandarin Tech project lies in its dual function. This massive structure is far more than a high-speed transportation corridor. Against the fury of the Java Sea, the expressway rises like a gigantic coastal fortress, built to absorb and resist the force of powerful storms and extreme tides, while shielding thousands of households behind the embankment from the recurring nightmare of coastal flooding. Looking back at the entire Mandarin Tech mega project, engineers around the world have to acknowledge it as a remarkable shift in both economic efficiency and mechanical performance. By eliminating the need for massive fleets transporting industrial steel, The project has saved billions of dollars in construction costs while making maximum use of a rapidly renewable local supply chain. Even more remarkable is the organic nature of the bamboo mat network itself. Its exceptional flexibility allows the entire underground foundation to bend and deform slightly, absorbing geological movement and the violent impact of ocean waves. Levels of motion that rigid concrete structures could struggle to withstand without cracking. But in the unforgiving world of infrastructure engineering, every breakthrough comes with its own trade-offs. Unlike steel beams forged in industrial furnaces to tolerances measured in millimeters, bamboo is an organic material, naturally inconsistent in shape and always vulnerable to decay unless it remains completely sealed within oxygen-poor mud. The long-term fate of this expressway therefore depends heavily on the workmanship of thousands of skilled hands, turning material selection and quality control into a relentless battle where even small defects can matter. And there is another limitation. This engineering solution is not a formula that can simply be copied anywhere in the world. It reaches its full potential only in specific coastal wetlands, where soft marine soils create the right conditions, and where nature has already placed an enormous renewable supply of bamboo close to the very landscapes most threatened by disaster. In the industrial age, humanity has always been obsessed with the desire to conquer nature. We forged solid steel, poured colossal concrete fortresses, and gradually forgot the simplest materials that had surrounded us for centuries. But the Semarang Demak megaproject delivers a powerful wake-up call to that way of thinking. A hollow-stemmed grass, once dismissed as a relic of the past, now stands proudly beneath the seabed, transformed into an enduring backbone capable of carrying the weight of an entire urban region. Semarang Demak is more than an expressway stretching across violent waves. It is a declaration of the 21st century, a place where human labor and one of nature's most primitive structures come together to reshape the way we think about construction. If this extraordinary fusion of nature and engineering has amazed you, don't forget to like, subscribe, and turn on notifications for Mandarin Tech. See you again on our next journey as we uncover more of the world's greatest technological masterpieces.